We figured out the uncertainty in parameter estimates when the noise is white noise. What if the noise is stationary, but it's not white noise? That means that we have autocorrelation of the noise, autocorrelation between different noise values. That's a pretty common case, and it's an important one, so it's something we should be prepared for. Well, the uncertainty of a regression parameter is still given by this formula. It's a sort of a total vector matrix product sum of the autocorrelation matrix of the noise times terms involving the dual trial vectors. However, we can't use the simple form we had before. When we had white noise, the variance-covariance matrix of the noise was sigma squared times the identity matrix, which is pretty simple. But now it won't be. I'm going to write it in this form. We're going to deal exclusively with the case of even time sampling. So the time offset between consecutive time measurements is always some constant. In that case, you may recall that the variance-covariance matrix of the noise for stationary noise is a symmetric Toeplitz matrix. That means that it really has this form. Toeplitz means that the values don't change as you move down and to the right or up and to the left throughout the matrix. I'll write it like this. The variance of a particular quantity is sigma squared. The covariance between a given noise value and the next noise value is sigma squared times rho 1, where rho 1 is the autocorrelation at lag 1. The covariance between a given noise value and the noise value 2 time steps later is sigma squared times rho 2, where rho 2 is the autocorrelation at lag 2. In general, the quantity rho sub j is the autocorrelation of the noise at lag j. Then, when we work out the uncertainty of a parameter estimate, it turns out to be this. It is sigma squared times a pair of sums added together. One of them is just the products of dual trial vector values. That's what comes from the diagonal entries in the variance-covariance matrix of the noise, those that are all 1 that end up being multiplied by sigma squared. The other term here, this double sum, is autocorrelation values times the sum of dual trial vector values times their time offset values, the lagged values. Those are the terms we get from the parts of the variance-covariance matrix of the noise that are not on the diagonal. These terms here and here. Incidentally, there's this factor 2 here because for each possible autocorrelation, there are 2 lines in the matrix corresponding to that. There is one line above the diagonal and another line below the diagonal. So the uncertainty in a parameter estimate is sigma squared times the sum of the squares of all the dual trial vector values plus twice the sum of all autocorrelations times the sum of dual trial vector values with time-lagged dual trial vector values. I'm going to take this term, this simple sum, and factor it outside the brackets to write it like this. Here's just that term itself. Of course, we get 1 here, and here we get this quantity where I've just divided by that double sum. This quantity that's outside the brackets, you may recognize that. That is the uncertainty in a parameter estimate for white noise. So the uncertainty of a parameter estimate for noise that isn't white but is still stationary is the white noise uncertainty times 1 plus these terms here, all of which involve autocorrelations. Now, the final term, by the way, is just the sample autocorrelation at lag j of the dual trial vector. You may even recognize that this is the Yule-Walker estimate. It is the sum of values with time-lagged offset values divided by that with no lag. So what we have is that the uncertainty of a parameter estimate is sigma squared times the inner product of the dual trial vector with itself times this correction factor, which is 1 plus twice the sum over all autocorrelations times autocorrelation times the sample autocorrelation at lag j of the dual trial vectors. Now we can use a couple of simplifications to make things a little bit easier and produce a formula that will be excellent in most, if not almost all cases. One is that it's the very common case that all the autocorrelations at all lags never go negative. Now that's not always the case, certainly not always the case. But in things like fitting slowly changing functions like a straight line or even a quadratic curve, it's a pretty safe assumption that the autocorrelations will not be negative, so we can treat them all as though they're positive. Another is something that we don't even have to consider an approximation, and that is that the sample autocorrelation of the dual trial vector at lag j is always less than or equal to 1. It cannot be more than 1. In fact, that's just impossible. If I use those two inequalities, I can transform my previous expression into an inequality. First, I can take this expression and I can take the sample autocorrelations of the dual trial vectors at lag j and just substitute 1 and know that that's an overestimate, so the true expression will be less than or equal to that. By the way, instead of writing the expected value of beta hat minus beta squared, I've just written delta beta hat. It's just an easier notational thing. So now I have an inequality where the uncertainty of a parameter estimate is less than or equal to its white noise value times a correction factor which is of this form. And notice this is a less than or equal to inequality, not an equality. Now I am just going to say that this sum goes up to n minus 1, which is the maximum lag between any two observed values. I'm going to say that the autocorrelations get smaller and smaller as lags get bigger and bigger. And by the time we get to very high lag, it's going to be pretty small. So we'll have a good approximation. Certainly, if all the autocorrelations are never negative, we have an inequality where we can still use the less than or equal to sign and use the same expression, only this time I've let the sum go all the way to infinity at all lags. Well, that's just the uncertainty for white noise times nu, with the Greek letter nu, which is that correction factor in here, which is the correction factor which involves summing up through all autocorrelations all the way out to infinity. Now, the reason that this particular expression can be so useful is that in many cases we can actually compute what that correction factor nu is. The first part, by the way, is what the variance of the parameter would be with no autocorrelation. The factor nu is, well, I call it the inflation factor of the parameter variance due to autocorrelation. Let's take an example where we can actually compute what it is. It's AR1 noise. We looked at that earlier. In that case, the autocorrelation at lag j is just equal to some constant rho to the power of j. In that case, the autocorrelation correction factor is 1 plus twice the sum from 1 to infinity of rho to the power j. Well, this is another one of those sums that you can work out by a familiar algebraic expression, and what you end up with is 1 plus rho divided by 1 minus rho. So when you are dealing with least squares regression on AR1 noise, a good way to estimate the uncertainty in your regression parameters is to compute what they would be for white noise and then multiply them times this correction factor. Note that by uncertainty I mean the squared uncertainty, or the variance. For the standard deviation, that would be the square root of the variance, so you would multiply the white noise standard deviation times the square root of this correction factor.